Hi everybody and welcome. My name is Lukas and today I will be talking about the developmental trajectory of object recognition robustness, and we will be comparing children, adults and convolutional neural networks. This is work I've been doing in collaboration with Robert Geiros and Felix Wichmann from the University of Tübingen. So, the term core object recognition refers to the ability to rapidly and effortlessly recognize objects across different identity-preserving transformations, such as variations in size, lighting, or orientation. In tasks measuring core object recognition, adults perform close to ceiling, and the same is also true for ImageNet trained CNNs. However, regarding distorted images, as the one below, things look quite differently. While human performance is robust against a wide variety of distortions, CNNs perform relatively weak in comparison, a finding which we here refer to as robustness gap. As a short demonstration of this gap, let us consider an application like the reverse image search of Google Images, which is under the hood using CNNs to recognize objects. So if you, for example, are feeding an undistorted image to Google Images, you will get a pretty neat result featuring many similar cars as the one on the input image. If you, however, are feeding a distorted image to Google Images, you will get a dramatically different result. You just won't get any cars. What you get is a bunch of images similar in texture and color. So the algorithm behind Google Images does not recognize the depicted object as a car. And accordingly, we wanted to investigate two possible reasons for this robustness gap. The first is that the robustness gap is due to a difference in quantity and quality of training data. The idea here is that humans just have seen a whole lot more of images than a standard CNN, and additionally also have gathered experience with naturally occurring distortions. Assuming that this hypothesis is true, we would expect robustness to be low in early childhood and then to continually improve during development as experience is accumulated. Another possible reason is that the robustness gap is explained by a difference in information representation and processing. Here the idea is that humans and CNNs just employ different strategies, which under certain circumstances result in different behavior. In this case, we would expect robustness to be already high in early childhood, as children and CNNs might employ different strategies from quite early on. In order to investigate those two hypotheses, we collected 22,000 psychophysical trials from children and adults on undistorted and distorted images. We tested 5 different age groups, which you can see here, and then compared the performance of these children and adults with 3 different ImageNet trained CNNs, which were VGG19, AlexNet, and ResNet50. To measure robustness, we applied 2 different distortions to ImageNet images. The distortions were eidolon and salt and pepper noise, which we applied to a varying extent, resulting in 4 difficulty levels for both conditions. We then used these stimuli in an image category identification task to test children and adults. Here you can see an example trial. First, the fixation stimulus was presented, which was then followed by the target stimulus, which in turn was followed by a 1/f pink noise mask. Then, participants had to indicate their response by choosing one of 16 categories. So let's move on to the results. Here you can see classification accuracy plotted as a function of difficulty level for the salt and pepper noise condition. While adults' performance is close to ceiling at difficulty level 0, there is a moderate decrease in accuracy as difficulty increases. But even at difficulty level 3, adults still show a quite high accuracy, which is far above chance level. However, considering CNNs, we find a quite different picture. While they also perform close to ceiling at difficulty level 0, there is a massive drop in performance already at difficulty level 1. And afterwards, CNN's performance approximates chance level as difficulty increases. So in this plot, you can see the already known robustness gap between humans and standard trained CNNs very clearly. Of course, the question now is, how did the children perform compared to adults and CNNs? Here is the data from the children split by different age groups. And as you can see, for almost all difficulty levels, accuracy somewhat increases as a function of age. However, already 7 to 9-year-olds show remarkable similar accuracy as adults. And most importantly, already 4 to 6-year-olds start to outperform standard CNNs at difficulty level 1, which means that there is already a robustness gap between very young children and CNNs. If we further consider normalized accuracy, which shows the change in accuracy relative to the initial accuracy at difficulty level 0 for each particular age group, we can see that all age groups show extremely similar robustness trajectories. So compared to their initial accuracy, already 4 to 6-year-olds show adult-like robustness. A similar but somewhat less pronounced result pattern was found for the eidolon condition. There is again a robustness gap between adults and CNNs, and again children start to outperform CNNs at a certain difficulty level, which here was at difficulty level 2. And again, normalized accuracy indicates that compared to their initial accuracy, all age groups show similar robustness trajectories. And perhaps you have noticed that ironically the oldest CNN, AlexNet, has the highest robustness. However, considering the other networks, the robustness gap becomes clearly visible at difficulty level 2. A further question then concerns the difference in absolute accuracy between the 4 to 6-year-olds and the other age groups. Is this difference either due to a general weaker ability to recognize objects, which would indicate a qualitative change in robustness, or is it rather due to a weak performance on a subset of categories, which in turn would indicate only a quantitative change in robustness? This could be, for example, due to the acquisition of more categories over the course of development. So in order to answer this question, we compared confusion matrices to investigate error patterns on a category level. Here you can see the confusion matrix for ResNet 50 at difficulty level 0. On the y-axis, you see the observer's decision, which in this case would be the prediction of the model. On the x-axis, you can find the presented category. So for example, all or almost all images of the category cat were correctly classified by ResNet 50. More generally speaking, high response probabilities along the negative diagonal indicate correct responses. Here now the confusion matrix for adults, which is actually very similar, and this is of course due to the close to ceiling performance of both observers. For the 4 to 6-year-olds, however, there are some categories which are harder to recognize than others. For example, images from the category clock are sometimes misclassified as keyboards. Jumping to difficulty level 3, we see that now there are huge differences between adults and ResNet 50. ResNet 50 becomes extremely biased towards a very small set of categories. For the 4 to 6-year-olds, however, we can see that response probabilities along the negative diagonal did not drop uniformly, but remain high for some age-appropriated categories such as bear, bicycle, car, or elephant. And this indicates that young children's weaker overall performance is not due to a general weaker ability to recognize objects, but rather due to a weak performance on a subset of not yet learned categories. And additionally, we can also see that children and adults show some similar confusion patterns, such as the car-truck confusion, as can be seen here. In other words, even though 4 to 6-year-olds have not yet acquired the same number of categories as adults, they are basically adult-like within those categories they already have acquired. In those categories, they reach similar high accuracy and also tend to make similar errors. And this suggests that the change in robustness is rather quantitative and not qualitative in nature. So confusion matrices indicate that while children and adults employ a similar strategy to recognize objects, standard CNNs are using a very different strategies in comparison. And from previous studies we know that this is at least true for adults. While they rely on shape to recognize objects, standard trained CNNs rely on texture to do so. So in the next step, we wanted to test on which cues children rely. To this end, we made use of a paradigm developed earlier, and thereby style transfer is used to combine the shape of one image with the texture of another image, in order to get a texture-shape cue conflict stimulus. If an observer now employs a shape-based strategy, he or she would recognize the cue conflict image as a cat. If, however, a texture-based strategy is used, it would be recognized as an elephant. And given the similarity in confusion matrices we found between children and adults, we expected children to rely on object shape too, just as adults. So in the plot here, you can see the fraction of shape and texture decisions within the responses that corresponded to either the correct shape or correct texture category. As we already knew, adults relied almost exclusively on shape cues to categorize objects. In contrast, and also as expected, CNNs show a very different pattern. They primarily relied on texture cues to recognize objects. So next, let's see what the children were doing. Very similar to adults, 13 to 15-year-olds relied primarily on shape cues, and the same was also true for the other age groups. So here the 10 to 12-year-olds, the 7 to 9-year-olds, and the 4 to 6-year-olds. Whereas the shape bias tended to increase somewhat with age, all children showed a strong shape bias. In other words, the strategy use of children in this regard is much more similar to adults than to CNNs. Taken together, we can say that even though object recognition robustness increases somewhat over the course of development, there is already a robustness gap between CNNs and children, and not only between CNNs and adults. And further, this change in robustness along the developmental trajectory seems to be of quantitative rather than qualitative nature. Children seem to have not yet acquired as many categories as adults, but within those they already have acquired, robustness is adult-like. And just as adults, and in contrast to CNNs, children rely on object shape rather than texture to recognize objects. And these findings lead to the conclusion that there is no evidence to support the claim that the robustness gap between humans and CNNs is explained by a mere accumulation of experience. However, there is evidence that children and adults employ a similar strategy to recognize objects, which is rather different from object recognition as implemented by current CNNs trained on ImageNet. And with this, I would like to finish and thank Robert and Felix for their amazing help and guidance during this project, and of course you for your attention. Thank you.